Somewhere between 60 and 80,000 years ago, a small group of humans left Africa and started walking. Not for adventure, not for curiosity, almost certainly for survival, chasing food, water, and better conditions across landscapes that stretched further than anyone in that group could have imagined. What they carried with them was dark skin. Deep, rich melanin built over hundreds of thousands of years to survive underneath one of the most intense suns on the planet. But somewhere along the way, as their descendants pushed further north into colder, dimmer, less sun-drenched parts of the world, something strange happened. Generation after generation, their skin got lighter and lighter and lighter again. So here's the real question this video is built around. Why did human skin color change so dramatically as our ancestors spread across the planet? And what does that transformation actually reveal about how the human body adapts to survive? Let's start with why humans had dark skin in the first place, because that part of the story is actually the simpler half. Early humans evolved in East Africa under intense, direct equatorial sunlight for an enormous stretch of evolutionary time. That sunlight brought a serious problem. Ultraviolet radiation, absorbed through the skin, can damage DNA. Specifically, it breaks down a molecule called folate, which is critical for cell division, healthy reproduction, and fetal development. Melanin, the pigment responsible for skin color, acts like a natural built-in sunscreen. The more melanin you have, the more effectively your skin blocks UV radiation before it reaches deeper layers and starts causing damage. Early humans with more melanin were significantly better protected against folate depletion, which meant healthier reproduction and, over generations, a genuine survival advantage. So dark skin wasn't just a side effect of evolution, it was a direct, essential adaptation to a specific environmental problem: intense equatorial UV exposure. For hundreds of thousands of years, that adaptation worked perfectly. Every human on Earth had dark skin because every human on Earth was living under conditions where dark skin provided a genuine biological benefit. Then humans started moving, and as they moved further from the equator into regions with weaker sunlight, shorter days, and much less UV exposure overall, that same adaptation that had protected them for so long started becoming a liability instead. Here's the problem. Melanin doesn't just block harmful UV radiation, it also blocks a different kind of radiation that the human body actually needs, specifically UVB rays, which trigger the skin to produce vitamin D. Vitamin D is essential for calcium absorption, bone development, and a functioning immune system. Without enough of it, humans develop serious, often fatal deficiencies: weakened bones, rickets in children, compromised immune function. In a place like equatorial Africa, sunlight is so intense and so consistent that even heavily melanated skin still manages to produce enough vitamin D. There's simply an abundance of UV radiation available every single day, more than enough to get through, even with strong natural sun protection in place. But in northern latitudes, that changes dramatically. Sunlight becomes weaker, days become shorter, especially during long winters, and the angle at which sunlight actually hits the ground becomes far more indirect, which means UVB radiation, the specific wavelength needed to produce vitamin D, becomes dramatically scarcer. So now you have a population with dark, heavily melanated skin living in an environment where sunlight is limited, and that same protective pigment that once saved lives is now blocking the small amount of UVB radiation available. The result, if nothing changed, would be widespread vitamin D deficiency, weakened bones, and a real measurable threat to long-term survival and reproduction. This is where natural selection steps back in, and it moves with a kind of brutal efficiency once you understand the mechanism. In northern populations, individuals born with slightly less melanin, meaning lighter skin, could absorb more of the limited UVB radiation available and produce enough vitamin D to stay healthy. Individuals with darker skin in that same environment were more likely to develop deficiencies that could seriously affect their health and their ability to reproduce successfully. Over many, many generations, this created consistent, measurable selective pressure. Lighter-skinned individuals in low UV environments tended to have better health outcomes and successful reproduction rates than their darker-skinned neighbors in that specific environment. It's important to say clearly, this has nothing to do with strength, intelligence, or any kind of hierarchy. It's a straightforward trade-off between two different survival pressures, UV protection versus vitamin D production, and different environments simply demanded different balances of that trade-off. The further north populations moved, the more that pressure built up, and bit by bit, generation after generation, skin color shifted, not through any conscious choice, but through simple, repeated differences in survival and reproductive success tied directly to how effectively different skin tones handled the specific light conditions of a specific place. This raises an obvious next question. If this shift happened purely because of environmental pressure related to sunlight, how do we actually know that? And more importantly, how fast did this change actually happen once early humans moved into these radically different environments?
Let's actually answer that, because the evidence here is more precise and more recent than most people expect. For a long time, scientists assumed that skin color changes happened gradually, smoothly, over an enormous span of time, tracking neatly with how far a population had traveled from the equator. But genetic research over the past 2 decades has revealed something far messier and honestly far more interesting than a simple gradient. One of the most surprising discoveries came from studying ancient DNA recovered from skeletons in Britain. Researchers analyzing a well-preserved skeleton known as Cheddar Man, dated to roughly 10,000 years ago, found something that genuinely upended assumptions. Cheddar Man, an early inhabitant of what is now England, likely had dark skin, dark curly hair, and light-colored eyes. 10,000 years ago, in Britain. Think about what that actually means. Populations were already living in northern Europe with dark skin, thousands of years after they had supposedly left Africa. The lightening of skin color in European populations didn't happen quickly or automatically the moment humans moved north. It took an enormous amount of additional time, and the genetic mutations responsible for lighter skin didn't even exist yet in that specific population. This tells us something important. Skin color adaptation wasn't one single event. It was a patchwork of separate genetic mutations arising independently at different points in time in different populations, all converging on a similar outcome, lighter skin, because they were all facing a similar underlying problem, low UVB availability. In fact, genetic studies have identified several distinct genes involved in skin pigmentation, and different populations around the world evolved lighter skin using different genetic pathways. European populations and East Asian populations, for example, both evolved lighter skin compared to their ancestral populations, but they largely did it through different genetic mutations arising independently. This is a phenomenon scientists call convergent evolution. Different populations facing a similar environmental problem arriving at a similar solution without sharing the specific genetic mechanism that produced it. That's a genuinely remarkable detail. It means lighter skin wasn't invented once and then spread outward. It was invented multiple times, independently, by different human populations, all responding to the same basic pressure of limited sunlight. Now here's where the timeline gets even more interesting, because some of these mutations are shockingly recent in evolutionary terms. One particular gene variant associated with lighter skin in European populations, often referred to by researchers studying it, appears to have spread rapidly across the population within roughly the last 5,000 to 8,000 years. That's not a slow, ancient process stretching back tens of thousands of years. That's a genetic change that occurred well within the span of recorded human agriculture and early civilization. Why would it happen that fast? One leading theory ties directly back to diet. As populations in northern Europe shifted from a hunting and foraging lifestyle toward large-scale agriculture, their diet changed dramatically. Early farming societies relied heavily on grain-based foods, which are naturally low in vitamin D compared to the fish, organ meat, and varied wild foods that many earlier hunter-gatherer populations consumed. This created a kind of double pressure. Weak sunlight limited how much vitamin D the skin could produce on its own, and a grain-heavy agricultural diet no longer supplemented that shortfall the way earlier diets had. In that specific situation, the pressure toward lighter skin and better UVB absorption would have intensified sharply and quickly, which lines up remarkably well with the genetic timeline researchers have found. This is a genuinely elegant piece of the puzzle. It's not simply humans moved north so skin got lighter. It's a combination of latitude, seasonal sunlight variation, and dietary shifts tied to agriculture, all stacking together to create strong, fast-moving selective pressure at a very specific point in human history. And it wasn't only European populations experiencing this kind of pressure. Similar processes played out independently in East Asia, where populations also evolved lighter skin, again through different specific genetic mutations than the ones found in Europe. Meanwhile, populations that remained in regions with consistently strong sunlight, much of Africa, South Asia, Australia, and the Pacific Islands, retained darker skin because in those environments, the original protective benefit of melanin against UV damage remained the dominant survival pressure with little competing pressure from vitamin D scarcity. So what we're actually looking at isn't a single story of humans lightening as they left Africa. It's multiple parallel stories, unfolding independently across different continents, different timelines, and different genetic mechanisms, all converging on the same basic underlying principle. Skin color across the entire human species tracks remarkably closely with the specific balance of UV radiation and vitamin D needs in whatever environment a population's ancestors happened to settle in. That raises one more genuinely fascinating question. If skin color is this responsive to environment, purely a biological trade-off shaped by geography and diet, what does that actually tell us about how meaningful or meaningless these differences really are at a deeper biological level?
That question turns out to have a genuinely striking answer, and it's one that a lot of people find surprising the first time they hear it clearly laid out. Skin color, despite how much social and historical weight humans have attached to it, turns out to be one of the most superficial traits in all of human genetics, in the most literal sense of that word. It sits right at the surface. A handful of genes controlling how much melanin gets produced and how it's distributed account for nearly all of the visible variation in human skin tone across the entire planet. Compare that to something like immune system genetics or the genetic variation involved in things like disease resistance, and skin color barely registers as a meaningful biological difference at all. Two people with very different skin tones can be genetically far more similar to each other overall than two people who share the same skin tone but come from different, unrelated populations. Skin color simply doesn't track with any deeper pattern of human genetic diversity. It tracks with one specific, narrow thing: how much UV radiation hit the skin of your ancestors generation after generation in whatever specific place they happen to live. This matters enormously because for a huge stretch of human history, and honestly in serious ways that continue today, skin color got treated as though it represented something deep, fixed, and meaningful about entire groups of people. Entire social systems, entire justifications for violence, slavery, and discrimination were built on the assumption that visible physical differences reflected something profound underneath the surface. But the actual science tells an almost embarrassingly simple story by comparison. Skin color is a localized adaptation to sunlight exposure. That's it. It's the same basic biological logic you'd see if you compared a polar bear's white coat to a grizzly bear's brown coat. It's environmental camouflage and radiation management, evolved independently multiple times in direct response to local conditions. It carries no deeper information about intelligence, ability, character, or worth, because biologically it was never designed to. It solves one specific physical problem, nothing more. And here's a detail that makes the whole picture even more interesting. Because skin color evolved independently multiple times in different populations using different genetic mechanisms, it means that two people with similar skin tones today might actually be using genetically distinct solutions to the exact same environmental problem. Their skin looks alike, but the underlying biological mechanism producing that appearance isn't necessarily shared at all.
evolution found more than one way to solve the same problem, and it used those different solutions in different corners of the world, sometimes producing remarkably similar-looking outcomes through completely separate genetic paths. This is where the real irony of the entire story sits. Humans spent thousands of years building elaborate social hierarchies around a trait that evolution treats as almost trivial, a surface-level adaptation to something as basic and impersonal as how much sunlight hits a particular patch of land. Meanwhile, some of the genetic changes responsible for this trait are shockingly recent, some occurring well within the last several thousand years, meaning that the specific range of skin tones we see across human populations today represents a relatively fast, still ongoing evolutionary adjustment, not some ancient, fixed, unchanging feature of different groups of people. So why did ancient humans go from dark skin to light skin in various populations around the world? The honest, evidence-based answer is this. As populations moved away from the intense equatorial sunlight of East Africa into regions with weaker sunlight, shorter days, and eventually grain-heavy agricultural diets low in vitamin D, natural selection favored lighter skin, because lighter skin allowed for better vitamin D production under those specific lower UV conditions. This happened independently, multiple times, in different populations using different genetic mutations, converging on broadly similar outcomes because they were all solving fundamentally the same underlying problem. There's something genuinely worth sitting with in that. The visible differences in human skin color that have carried so much unearned social significance throughout history are, underneath everything, a story about geography, sunlight, and a molecule called vitamin D. Nothing more profound than that. A biological trade-off repeated independently across the world, wherever humans happen to settle, shaped entirely by how much sun hit the ground where their ancestors chose or were forced to live. Every shade of human skin on the planet today, from the darkest to the lightest, and everything in between, traces back to the exact same evolutionary logic: adapt to the light available or don't survive as well as those who did. That's the whole story. Nothing more complicated and nothing less remarkable than that.